let's take a look at cosmology. Cosmology is the study of the universe as a whole, so not just the pieces inside of it, like stars, galaxies, planets, whatever, but the entire universe. And before we get into it, let's look at something called redshift. So, redshift is related to the idea that when you see an object moving toward you, it will appear bluer. And what I mean by that is that the light that you receive from an object moving toward you is shifted to smaller wavelengths. And an object that moves away from you, the light that you receive from that will be redder than what was emitted. The light is shifted to longer wavelengths. And this is just an expression of the Doppler effect, the idea that if an object moves towards you, the wavelength of the waves that you receive are going to be smaller, and if an object moves away from you, then the wavelengths of the objects that you receive are going to be larger. So when astronomers observe a galaxy, they can tell whether or not the galaxy is moving toward us or away from us, and how fast it's moving toward us or away from us, by looking at the absorption lines from that galaxy. So for instance, we know that hydrogen emits at 656.3 nanometers. If you observe a galaxy and you see that the wavelength of that absorption line is actually a little bit smaller, then that means that the galaxy is moving toward us. And if the absorption line is actually at a longer wavelength, that means that the galaxy is moving away from us. And there's an equation to show this. I'll write it down here. Z is equal to delta lambda over lambda, which is approximately V over C. So Z here is called the redshift, and that is the ratio of the change in the wavelength to the wavelength. The change in the wavelength is how much the wavelength that you're observing has shifted. Lambda here is the original wavelength that it should be emitted at. V here is the speed of the object, whether it's moving towards you or away from you, and then C is the speed of light. So Edwin Hubble observed the redshift of many galaxies back in the early 20th century. And when he did that, what he noticed is that almost all galaxies are moving away from us. That's a little bit odd. He also noticed that their velocity is proportional to their distance from us. So more distant galaxies are moving away from us at a faster rate. Okay. This led to something called Hubble's law. And if we draw a graph of the speed of the galaxy moving away from us versus the distance of the galaxy, the slope is called Hubble's constant. Hubble's constant, if we calculate it, is approximately 70 kilometers per second per megaparsec. So what that means is for every megaparsec that you move away from the Earth, the recessional speed of a galaxy increases by about 70 kilometers per second. And it's important to note that this 70 kilometers per second per megaparsec value is an estimate. Different studies have shown slightly different values. This is a very difficult observation to do because you have to somehow calculate the distance to a galaxy, which is not an easy matter. And you also have to accurately measure the speed of the galaxy, which requires some pretty fine measurements. But no matter. We get about 70 kilometers per second per megaparsec. So why is this? Why are almost all galaxies moving away from us? Are we in the middle of the universe and everything's just moving away from us? No. If we were in another galaxy, we would see exactly the same thing. If we were in this galaxy right here in this picture, it would seem like everything is moving away from us. And if we were in this galaxy over here, it would also seem like everything is moving away from us, and the further away something is, the faster it's moving away from us. The only way that this can be, or the simplest explanation for this at least, is that the universe itself is expanding. And one way that you can think about it, a good analogy, is it's kind of like a loaf of raisin bread put into the oven. If you are a raisin in the loaf of raisin bread, and when it's in the oven, the raisin bread is expanding, it would seem to every single raisin in that raisin bread that every other raisin is moving away. Every raisin would see that. And every raisin would see that the further away another raisin is, the faster it's receding. That's a pretty good analogy to what we observe when we look at other galaxies. Now, there are some pretty important differences. The raisin bread is expanding into the relatively empty space in the oven, but our universe is not expanding into empty space. Instead, Space itself is expanding in our universe. It's not expanding into anything. It's just expanding. All space is expanding. That's hard to imagine. But that's the simplest explanation for the observations. All right, so the universe is expanding. That means that if we go back in time, if we think back to the past, the universe must have been smaller than it is now. And if we kind of run the clock backwards, the universe would shrink back to a single point. The motion of galaxies suggests that about 13 to 14 billion years ago, everything in the universe was contained in a single point. And if we go back that far, if all of the matter and all of the energy was contained in a very small volume, the early universe must have been very, very dense and very, very hot. And this start to the universe is called the Big Bang. Immediately after the Big Bang, all of the universe was contained in a very small volume. It was very, very hot, very, very dense. And as the universe expanded, the density decreased, the temperature went down, and eventually galaxies formed, stars formed, and we reach the present day where we observe all of the galaxies moving away from each other. Now, it turns out that we can use Hubble's law to get a pretty good estimate for the age of the universe. And it goes like this. V is equal to Hubble's constant times d, where v is the recessional speed of the galaxy and d is the distance of the galaxy. Well, if a galaxy is moving away from us at speed v, and we're assuming that it's always been moving away from us at speed v, then the distance that it's traveled since the beginning of the universe is v times t. So if we put this into the Hubble equation, we get v is equal to the Hubble constant times v times t. So the v's cancel out. We get 1 is equal to the Hubble constant times t. So t is equal to 1 over the Hubble constant. Now, t is the time that it's taken for that galaxy to travel from our location to a distance d away. Well, it was at our location at the Big Bang, and now it's at distance d. So t here is the age of the universe. 1 over the Hubble constant, well, the Hubble constant is approximately 70 kilometers per second per megaparsec. 1 over the Hubble constant doesn't really seem like it should have time units, but it does. You got to do some unit conversions. You got to convert kilometers to seconds. You got to convert inverse megaparsecs to inverse meters, and then you get something that's in inverse seconds, and you take the inverse of that, and it's in seconds, and you got to convert it to years. It's a lot of work. But if you do that, you get approximately 14 billion years, which is a pretty good estimate for the age of the universe. All right. Now, let's think about something called cosmological redshift. So it turns out that the redshift of light is not just due to the motion of a galaxy away from us. It's also due to the idea that space is expanding. The wavelengths of light from distant objects are also made greater, they're reddened, by the expansion of the universe itself. And one way to think about this is, as light is traveling through space to us from a distant galaxy, the distance between the peaks and the troughs actually increases because space is expanding, it's stretching. So the wavelength of the light also expands and stretches, which increases the wavelength. This is called the cosmological redshift. And another concept we can think about is the cosmic scale factor. Cosmic scale factor is the factor by which the universe has expanded. And the justification kind of goes like this. So redshift z is equal to the change in the wavelength over the original wavelength. Well, the change in the wavelength is equal to the change in the scale factor over the original scale factor when the light was emitted. So we can rearrange that. We can write it this way, r minus r0 over r0. R over r0 minus 1 is equal to the redshift. The r in this equation represents the scale factor today. The r0 represents the scale factor of the universe when the light was emitted. So the Big Bang is pretty much accepted science now, but at the time it was proposed, it was considered a radical idea, and it was not immediately an accepted theory. One of the ways that it became accepted is through prediction and observation. So it goes like this. If the universe started as a Big Bang, then when it was very young, It was very, very hot and very, very dense. So the universe must have emitted light. And because the universe was very, very hot and very, very dense, it must have emitted a huge amount of light at very small wavelengths. If you think back to the black body, if it's at a high temperature, it emits very small wavelengths. But the radiation from the beginning of the universe must have been redshifted over time. Just like the light from faraway galaxies, the light from the early universe must have been redshifted. And it must also be pretty dim, because it's coming from so far away. At least the light that we would receive right now would be coming from very far away. And in fact, if you do the calculation, the light from the very young, hot universe should have been redshifted all the way into the microwave part of the spectrum. This idea was predicted that if the universe had been very, very hot right after the Big Bang, we should be receiving something called the cosmic microwave background. This is the light from the early hot universe that has since been redshifted into the microwave part of the spectrum. So that was proposed. For a while, it was not observed. People looked for it and they didn't see it. Then in 1964, two guys, Penzias and Wilson, were doing an experiment that had nothing to do with cosmology. They were actually studying telephones and how to transmit telephone signals. But they observed the redshifted light from the beginning of the universe. At first, they didn't know what it was. When they did the observations, they thought it was pigeon poop in their detector. But it wasn't pigeon poop. It was light from the early universe. And that was very, very strong evidence for a young, hot, expanding universe. And they both got a Nobel Prize in 1978 for it. Since then, there have been very detailed observations made of the cosmic microwave background, often from satellites, such as the Cosmic Background Explorer, or COBE, or the Planck satellite. And these satellite observations have shown that the cosmic microwave background looks like that from a black body at a temperature of 2.74 Kelvin. Now, the cosmic microwave background was not created by an object at 2.74 Kelvin. It was created by the early hot universe, which is at a much higher temperature. But the light from that early universe has been redshifted. And in being redshifted, it now appears much redder. It's in the microwave part of the spectrum, and so it looks like it's coming from a much cooler object. But the bigger point is that once upon a time, there were many theories about how the universe began, and the Big Bang Theory was just one of them. But the Big Bang Theory was different because it suggested, or it predicted, that we should see a cosmic microwave background. Later on, the cosmic microwave background was observed, which was considered pretty strong evidence, and is still considered very strong evidence, that the universe did begin as a Big Bang. Cosmologists, of course, are always gaining new observations and adapting the theory, and one adaptation that they've had to make is based on observations of a type of supernova called Type 1a supernova. And when they look at Type 1a supernova, it turns out that it seems like the universe is not only expanding, its expansion is accelerating. The reason for this acceleration and the expansion has not been explained. That's still an active area of research in cosmology. But right now, the name given to the cause, even though we don't know what the cause is, the name given to it is dark energy. And if the name sounds mysterious, it should. Scientists have not come to a conclusion about what the dark energy is. There are many ideas out there, but like I said, this is still a very active area of research in cosmology.